In this class, we are going to see subgroups of Z. So, we have to show that the collection Nz, which is equal to set of all nk such that k belongs to Z, you can also call it as multiples of n in Z, is actually a subgroup of Z. Now, in order to show it is a subgroup, we are going to take the help of subgroup test that we have proved in the previous classes, that was one step subgroup test. We are having two step as well. We are going to discuss it afterwards. So, what does the one step subgroup test say? First of all, we want group G definitely, and in order to prove H is a subgroup of G, first of all we are supposed to show that H is non-empty, H is a subset of G, then we can use that one step subgroup test, because these are the assumptions of that test. Once we prove that H is non-empty and H is a subset of G, then the test says take any two elements of H and prove that AB inverse lies in H, and this much is sufficient to conclude that this H is actually a subgroup of G. But remember, in additive groups this condition is slightly different. So, take two elements of H and we should prove that A minus B belongs to H in case of additive groups. Why? Because in additive groups B inverse is actually nothing but minus B. Now here we know that Z is an additive group, so we are supposed to use this one, that is AB belongs to H implies A minus B belongs to H, in order to show this collection is actually a subgroup of Z. Now let us try to prove that the set Nz is non-empty first, right? Because that are the assumptions of our one step subgroup test. Now why this Nz will be non-empty, whatever may be the value of n. Let us try to fix some value of n and try to understand what does this set look like. So, if I fix my value of n to be, let us say 1, then this Nz is actually equal to Z, and we already know the elements of Z, right? So, if I fix my value of n as 2 now, so we will get 2Z. So, 2Z will be actually collection of what? This will be 0, 2, 4 and so on. On the negative side, minus 2, minus 4 and so on. So, basically we are taking multiples of 2 here. What we have to do? We have to multiply each and every element of Z by 2. That is exactly what I have done. Now, if n is equal to 3, then what will be my 3Z? Again the same logic, multiply each and every element of Z by 3. So, starting from 0, so that will be 0 only, right? So, 3 multiplied by 1 will be 3, 3 multiplied by 2 will be 6 and so on. On the negative side we will have minus 3, minus 6 and so on. Definitely you can have the value of n to be 0 as well. In that case we will have 0Z. So, what will be my 0Z? So, in other words, we have to multiply each element of Z by 0. Ultimately we will get 0 only, right? So, that is nothing but singleton 0. So, if we observe these sets properly, in each and every case one element is always present, and which is that? That is nothing but what? Absolutely, that is nothing but 0. Because we can write 0 as a multiple of n all the time, right? Because Nz is a collection of multiples of n, so for 0 to be in Nz, we should be able to write it as a multiple of n, right? So, I will say here as 0 can be written as n multiplied by 0 therefore 0 will be a member of nz and therefore nz will be non-empty. So this part is clear. Now next thing is we have to show this nz is actually a subset of z, because we are proving nz is a subgroup of z, right? But that will obviously happen because n is a member of z, this k is also a member of z, so this collection nk is going to be an integer again. So I will say clearly this nz is actually a subset of z. Now we will move towards proving our main condition. So we will start with any two elements of nz. So I will call them as AB. So I will say let AB belongs to nz be any elements. But what does it mean? As A and B are in nz, but remember, how does element of nz look like? It is a multiple of n, right? Let us try to understand it through example. So if I take any two elements of 3z, what does it mean? Either it will be 6, right? Either it will be 9, it will be 12, right? So let us say this is my A, this is my B. So as we can observe, since these are elements of 3z, we can always write them as multiples of 3, right? So 12 can be written as 3 multiplied by 4 and 6 can be written as 3 multiplied by 2. So this is about multiples of 3. So talking about multiples of n, this A can be written as some nk1 and B can be written as nk2. Remember, this k1 and k2 may be different, right? So I will say for some k1 and k2 belonging to z. Now what we have to show? We have to show that this A minus B is actually a member of nz again. But in order to show it, what we have to show? We have to show that this A minus B is a multiple of n, right? So I will start with A minus B. So I will say consider A minus B. We already know the values of A and B. We can just put that values. So nk1 minus nk2, and which is actually n k1 minus k2, and we can call that k1 minus k2 as some k3, where k3 is k1 minus k2, which is also an integer. So we have shown that this A minus B is also a multiple of n, and therefore this A minus B belongs to this nz, and therefore nz is actually a subgroup of z. Okay, that is what we wanted to show. Yeah, this is a notation for subgroups.